All right. Yep, just start a pile. Nope, not in there. Okay. Not in there. We'll start it like this for me. Thanks, Bella. Okay, so last time we talked about the test format, right? And I think you guys got to assign the review pack and all that jazz, right? Do you guys have questions on stuff, homework, review, test format, anything that you might want to ask questions about here before we start in on chapter 2 stuff? Okay, fair enough. That is okay. Today we're going to do section 2.1. Quick question for you guys. Is anything we do today going to appear on the test? No. It's chapter 2, right? Chapter 1 is the test. Chapter 2 will be the next test. So even though we haven't taken the chapter 1 test yet, nothing that we do today will be on the test. Cool? Okay. I just want to, just trying to be clear, right? Most of you guys don't know me, so we want to be clear. All right. So in chapter 2, we're going to start building out our subject of trigonometry here in earnest. So the first section here, we're going to talk a bit about angles. And I want to just kind of recall why that's important. So in geometry, you guys talked about the sine, cosine, and tangent operations. In geometry, sine, cosine, and you can take sine, cosine, and tangent of what kind of number? What kind of number can we plug into sine, cosine, and tangent? So it has to be an angle measure. Okay. More specifically, where does that angle measure have to come from? Can I put any angle measure in there? No. Where did that angle measure have to come from? In a triangle. What kind of triangle? No, you're doing good. You're doing good. What kind of triangle do we need to have? Right triangle. And can I pick any of the angles from the right triangle? No, I can't pick what angle? Can't use the right angle. Yeah, so we have to have these x's are acute angles from a right triangle. Okay. So what we're going to be doing in chapter 1 is we're going to be extending our definitions of sine, cosine, and tangent so that we're not limited to this geometric definition for sine, cosine, and tangent, that we can break outside of acute angles from right triangles and begin to use sine, cosine, and tangent on any kind of angle we'd like. Okay? So we're going to start by just kind of talking about angles in general, since that is the input for sine, cosine, and tangent. So in geometry, what unit did you use to measure angles? Degrees, right? Would you believe there's actually other ways to measure an angle? there are, when I ask you, like, what is a degree other than a way to measure a triangle, if I ask you to define, like, what is 1 degree? It's kind of a tough question, right? Like, it's like, well, how long is a meter? Just like it's this long. So we're going to talk about another way that we can measure angles today. That's called the radian. That's another way that we can use to measure an angle. And there's actually a third way to do that called a gradient. But that's not something we do in a high school classroom. So we're not going to worry about that. So degrees we kind of know about already, right? We understand kind of intuitively like what a 60-degree angle would look like versus a 10-degree angle versus a 120-degree angle. Everybody kind of have a sense of that. I'm hoping you could draw me a reasonable, like a picture reasonably close to one of those. You know what I mean? Particularly if you had a protractor. Probably be pretty easy then. So what we're going to focus on today is this new measurement for angles called the radian. So we're going to start with what you don't have for degrees, because I don't think we ever in geometry define what actually we mean by a degree. We just start using it. So we say a central angle has a measure of 1 radian. If it intercepts an arc with the same length as the radius. Now, this is a lovely specific definition, but Mr. Kulik, I don't remember what half of the words in this mean because these sound like geometry terms to me. So let's kind of go through that. Oops. So when we say a central angle, what are we referring to? We're referring to an angle whose vertex is at the center of a circle. So let's say that's the center of my circle there. I'll call this circle A. So I can draw, some angle whose vertex is at A. That's a central angle. Then I say, if it intercepts, what does intercept mean? Yeah, Ryan? Yeah, crosses, runs into, intersects, all of those are equivalent. Okay, so it's got to run into something or cross something. It says it's going to intercept an arc. What is an arc? It's part of the perimeter of a circle. So if I called this point B and this point C, we'd say that arc BC is that. Everybody's okay with that? Okay. So what this definition is saying, it says that if the length of AB, well, or I should say if segment AB is congruent to segment BC, then the measure of angle BAC is equal to 1 radian. Is everybody okay with that? So if this length and this length are the same, then that angle measure is 1 radian. Okay, well, that's a super clear or super specific definition of what a radian is. I mean, we can debate how clear it is, maybe. But it's super specific, right? We know exactly, like, okay, if you want to talk about how big 1 radian is, I can construct this situation, and then you could measure it, right? To see visually what it is. So this now presents us with a second way of measuring an angle, right? So we have degrees, and now we have radians. When we have 2 ways of measuring something, what's the first thing we would ask for after that? So you have like a way to measure height in feet and in meters. What would you immediately ask for after presented with 2 ways of doing something? How do you go back and forth between the 2, right? Like, how do I convert from feet to meters or meters to feet? How am I going to convert from degrees to radians or radians to degrees, right? If you have 2 ways of measuring something, automatically we're going to want to have a way to go back and forth between them, between degrees and Celsius or Fahrenheit and Celsius in temperature or whatever it is that we're measuring, right? It's like the first thing we want to have. Oops. Okay. So let's say that we have our circle. Yes.
Can I go to the IT department and pick up my service?
Oh, sure. You're welcome. So we know that from our definition, if we say that arc B, the measure of arc BC is equal to the measure of segment AB, then the measure of angle BAC is equal to 1 radian, right? So we're saying that if the measure of arc BC is equal to 1 radius, then that angle measure should be 1 radian. That's going to be kind of our conversion idea, that an arc length of 1 radius is equal to 1 radian. So now let's take another example here. Okay. So let's make this our central angle. What's the measure of BAC in degrees? $180. Great. How'd you know that? It's a straight line, has 180 degrees, or you could know that it's half the circle and a circle has 360. Yep. Either one is okay. And what's the measure of arc, or how long is arc BC? It's not going to be a number we're looking for. Well, it's not 1 radius. How much of the perimeter is BC going to be? Half, right? How do you find the perimeter of a circle? Many of you took an ACT last weekend. You should probably remember this still. The perimeter of a circle, or circumference. Ryan? 2 pi r is correct. Well done. Everybody's okay with that. So we have an arc length that is pi radius, or pi radiuses. I guess the plural for radius is radii. Everybody's okay with that? That arc length is pi radii long. Using this, how many radians is angle BAC? If 1 radius gave me 1 radian for the angle, how many is pi radius or radii going to give me in radians? Pi radians, right? If 1 radius gave me 1 radian, pi radii should give me pi radians. It's just like a 1-to-1 relationship. Everybody's okay with that? So we know that angle BAC is 180 degrees and it's pi radians. So what does that tell me then? Is that 180 degrees is equal to pi radians. That's my conversion factor to go from degrees to radians or radians back to degrees. Everybody okay with that? Let's practice doing a conversion then. So what if we want to go from 90 degrees to radians? How many of us are currently in or have ever been in chemistry? A lot of us, most of us. What we're going to do here is just like your basic unit conversion. So we're going to start with 90 degrees, and we're going to multiply it by some conversion factor so that the answer we're left with is in radians. If I have degrees on top, what unit should be in the denominator? Degrees also, right? And in our case, that's specifically 180 degrees. And what should be on top of 180 degrees? The other half of my conversion factor, which would be pi radians. Everybody okay with how I set that up? So just like in chemistry class, the units are going to cancel, so degrees cancels with degrees. And then I can reduce this fraction since I'm multiplying. 90 goes into 180 2 times. So I have 2 times pi divided by 1 times 2. So pi over 2. And the only unit I have left is radians. So my answer is pi over 2 radians. Or, how else could I write this? As a decimal, right? So I could write this as pi over 2. And I get about 1.57. The pi over 2, we would call that an exact answer because there was no rounding involved. We wrote it in terms of pi. The 1.57 would be the rounded or the approximate answer. Depending on the directions in your question, one or the other might be appropriate. Which one do you suppose Mr. Kulik prefers if not given an option? The exact one. Okay? You are correct. Let's do another. Let's say we want to go 152 degrees to radians. I'm going to set this up the same way. And because I'm going, again, from degrees to radians, I know the conversion factor I'm going to be using will be exactly the same, right? So far, so good? Let's see. Degrees cancels with degrees. 52 and 180 are both even, so I know that a 2 goes into each of those. And 76 and 90 are both even, so I know a 2 is going to go into each of those. 36. Or 38. And then 38 and 45 don't share any common factor, so I know that I'm done reducing. Is everybody okay with that? So now I can multiply straight across. So 38 times pi is just 38 pi. And 1 times 45 is just 45. I just divide by 2. Because they're both evens, right? 152 divided by 2 is 76. 180 divided by 2 is 90. And then they're still even, so I could do it again. Giving me half of 76 is 38, and half of 90 is 45. At that point, I could tell that there were no more divisors, common divisors. The only divisors of 45 are 5 and 3. It's easy to tell that 38 isn't divisible by 5 because it doesn't end in 5 or 0. And it's easy to tell 38 isn't divisible by 3 because the sum of its digits, 3 plus 8, is not divisible by 3. That trick only works for 3s, but it's a good one. Or I could have typed this into my calculator. And that's about 2.65 radians. Again, depending on the directions, might call for an exact answer or a rounded answer. Just would depend on your directions, which one you'd want to do. If you're given the choice, then I would accept either, although Mr. Kulik prefers exact. Yeah. What if we want to take 2 pi over 5 radians and go to degrees? So here we're going the opposite direction. So I'm going to start by writing this as 2 pi radians, divide by 5, and I'm going to multiply it by my conversion factor so that at the end I get degrees. Since I have radians in the numerator, what unit needs to be in the denominator? Radians. And my conversion factor is that pi radians is the same as 180 degrees. So when I multiply, the units can cancel, and then the pi's can cancel. And then I can reduce the 5 and the 180. 5 goes into 180 36 times. So I have just 2 times 36, which is 72, divided by 1 times 1, or just 72 degrees. Notice that I only got an exact answer here. There's no approximate possible, since the exact answer was already reduced as far as it could go. There's no decimal approximation for that. Everybody's okay? We'll do one more. So what if I have 1.6 radians and I want to convert that to degrees? Well, still kind of starting the same way. Notice here is the same kind of problem as the previous one where I'm going from radians to degrees. So I know immediately I'm going to be using the exact same conversion factor. So radians cancels with radians. And then I have 1.6 times 180. That's going to should come out to be something with no decimal in it. Yep. So I could write that as 288 over pi. Do you suppose, or in your geometries, have you ever seen an angle measure written like that? 288 over pi degrees? No. And really, we wouldn't ever write it this way. Degrees are almost always going to be represented as a decimal as opposed to like a kooky looking exact number like that. So as a decimal, 288 over pi is about 91.67 degrees. So if you're representing something in degrees, almost always are we going to want the approximate value. Degrees are something that we have a good visual indication of like how big of an angle that is, right? With radians, it's like 3 pi over 5 radians. I don't know how big that is any better than I know that like, that it's going to be like 1.9 radians or whatever. Like, doesn't make any difference to me. It's like the same, you know what I mean? Equally as meaningless. But degrees, 288 over pi means nothing to me. 91.67, I know immediately like what shape of angle I'm talking about there. Okay. Using a simple rearrangement from our definition of a radian, we can make the following definition. If a central angle that I'm going to represent with the variable theta there, that's the Greek letter. It looks like a 0 with a horizontal line through it. That I've measured in radians. We'll put the comma there. In a circle with a radius r, then the length of the intercepted arc S is S equals R times theta. You okay there, coffee? Okay. Just checking. It sounded like a rough one there. Okay. So what is this saying here? Let's just kind of draw a picture. So here's our central angle, BAC. So that's my theta. AB is my radius. And then BC is my arc length, is the length of that intercepted arc. What we're saying is that that arc length can be found by doing R times theta, presuming that theta is written in radians. If I wanted to write, or if I was given theta in degrees and wanted to find the arc length, what would I have to do? Well, I'd have to convert theta into radians by multiplying it by pi over 180. Or you could write this as like R pi theta, or R theta pi over 180. So the unit that the angle is measured in directly affects the formula that I'm going to use to calculate this arc length. Let's do some examples. Sound good to you guys? Yeah, it's good because you didn't have a choice. That's what we're going to do anyways. Ha 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 ha. mean, I guess you did have a choice. You could have like stood up and left or something, but that's not really a choice. It's just a bad one, right? All right. Oh, one thing when I'm writing these angles in radians, so here I wrote theta equals 0.98 radians. Eventually, we're going to stop. I'm going to just stop writing radian after things that are in radians. How are you going to know the difference between an angle in degrees and an angle in radians? The degrees have a degree sign next to it. The radians will have no symbol next to it, rather than just continue to write RAD afterwards. Now, we'll continue to do that here for a day or two. We'll keep writing radian after radian angles, but eventually I'm just going to quit doing that. Is everybody okay with this? So you do need to be careful that on angles that are measured in degrees, you're remembering to write the degree symbol, because that is how we're going to tell the difference between a radian angle and a degree angle. Okay. Anyways, back to our problem. Since our angle is in radians, I'm going to use the formula S is equal to R times theta. So I just type that in to my calculator, and I get the number 1.372. What unit should be attached to this number? Is the length of that arc. What unit should get attached to this number? What other length unit did we use in this calculation? Meters, right? Radians isn't a length that's like the size of an angle, but meters measures length, right? This should be meters. Just matching the unit that I used in the calculation. Okay. Yes, sir. Of course. Let's take a look at this one. We're solving for S when R is equal to 3.8 inches and theta is equal to 40 degrees. What's the thing you have to immediately recognize in this problem? The angle is measured in degrees. That means I have to use the other formula. Yes. Sure. But after I've done that, oops. Goodness gracious, Mr. Kulik. You know, sometimes we just have one of those days. And when I type that all into my calculator, I get about 2.653. And what unit should I attach to this? Inches. Very good. should match the unit of length in my calculation. What if we alter the problem a little bit? And instead of giving you r and theta, we give you s and theta and ask you to solve for r. Oh no! It's so much harder. It's not any harder. We start the same way. What's the first thing we need to check? Great, the unit of measurement on our angle. In this case, that's radians. So we'll use the radian version of our arc length formula. Now we can fill in our values. 18 goes in for S. 2.13 goes in for theta. So if I divide both sides by 2.13, I get that r is equal to 18 over 2.13. And when I type that into my calculator, I get about 8.45. And what unit should I put on this? Centimeters. Again, that's a radius, so it should have a length unit attached to it. The length unit in this problem was centimeters, so it should be in centimeters. Everybody's okay with the calculations we've done so far? These are pretty simple calculations so far, right? We're just using a formula and plugging stuff in. Let's do another example that's maybe a little bit trickier. So what if I ask you to find the perimeter of a sector with a central angle of 1.7 radians, cut from a circle with a radius of 5. What word in here is the big catch that maybe we don't remember what that is? Sector. Yeah, exactly right. Sector is a geometry term that maybe we don't remember. Does anybody remember what a sector is from geometry? Okay. Well, a sector is just a pizza slice. So if like this is our pizza, this is our pizza slice. That's our sector. Actually, let me draw that in yellow since it matches with the word I've highlighted. It's just a pizza slice. So the perimeter for that sector is going to be the length for AB. Let's write it this way, I guess. Plus the length for AC, plus the length for BC. Everybody agree with that? That that's what a perimeter is, just the distance around? Okay. How long is AB? AB. How long is AB? Start there. Should be able to do it with no calculation. It's just a reading skill. 5. Very good. How do you know it's 5? Yes, it's the radius of the circle. So we know that that's 5. Similarly, we know that AC is 5, right? Because they're both radii of the same circle. Oh, this is going really well so far. And then how am I going to calculate BC? BC is an arc length, so I should use my arc length formula. Since theta is given in radians, I get that, and I think I am good to go. Oh, I didn't give a unit for these radians, or the radius, huh? Let's make those centimeters, I suppose. So this should be centimeters. Oh, Mr. Kulik, that wasn't too bad once I remembered what the definition of what a sector looked like. The trick there, a sector is just a pizza slice. Just a pizza slice. From a round pizza. We're not talking Jets pizza slices here. Or Buddies, or whatever your square pizza preference is. Talking about those roundies. Everybody okay there? So far, so good? One more example, we'll be stopping for today. We can take the rest of the time for you guys to relax or whatever, but we lost like, I don't know, I lost like 30 or 40 minutes from the A class because it was right after Mass. So we're just going to jog in place and you'll have a little bit of free time to kind of get caught up on whatever you need to. Sounds like some of you guys, based on my stack of notes here, might need some time to get your notes straightened out here. So that's probably a good thing. All right, one more example. A car has 18-inch diameter tires. If the car is traveling at 15 miles per hour, how many revolutions per second are the tires making? This guy right here is a pure unit conversion problem. So we're going to start with 15 miles per 1 hour. We're going to do a whole string of conversions and end up in revolutions per second. Oh boy, Mr. Gulick, that looks like a lot. You've left a big space there. Yeah, there's a couple of conversions in here. First thing that I would notice is that my denominator is currently hours, and at the end, my denominator needs to be seconds. Well, that should be easy to take care of. I'm going to just convert hours into seconds. I don't know how many seconds are in an hour, but I know 1 hour is 60 minutes. And I know that 1 minute is 60 seconds. So now my unit in the denominator is seconds. So I'm good with that. Everybody okay with how I did that? Just a basic unit conversion. Hopefully we all remember how many seconds are in a minute and how many minutes are in an hour. That's common, right? All right. Here's the tougher question now. Is somehow we got to convert miles into revolutions. How am I going to convert a linear distance, like a mile, into a revolution, which is like a circular motion? Here's the trick. One perimeter, or circumference, is equal to one revolution. Oh, okay. What shape is spinning? A tire, so it's a circle. And how do I find the perimeter of a circle, or the circumference of a circle? 2 pi r. Okay, and what is the r in this case? The radius of the wheel, which is?
You literally just found it out and I can't find it. It's so now
9 inches. Everybody's okay with that? Well, the 2 pi r, r is radius. I'm given the diameter is 18, so the radius is half the diameter. That's how I got to 9. I tried to color code the pieces that went together, right? The piece from the description that gave me the 9. Okay, here's the problem though. What unit is my length currently in? Miles. What is my circumference written in? What unit is my circumference written in? Inches. So what am I going to have to do before I can use this conversion factor? I have to convert miles into inches. Well, I don't know how many inches are in 1 mile. But I know that 1 mile is 5,280 feet. And I know that 1 foot is 12 inches. So miles cancels with miles, feet cancel with feet. And now I'm in inches. Everybody's okay with that? Now it's time to use this conversion factor down here. So I can say 18 pi inches is 1 revolution. So the inches cancel, and I'm left with revolutions. Yes! Now all I have to do is multiply this through. So I'm just going to use one fraction on my calculator because I know when I multiply fractions, I'm just multiplying the tops together, right? And anything that's a 1, I'm going to ignore. So I'm just going to write 15 times 5,280 times 12. And then on the bottom, I'm going to have 60 times 60 times 18 pi. And when I do that, I get about 4.67 revolutions per second. Is everybody okay with that? Does this look a lot like a unit conversion chemistry problem that you guys would have done? Very much so, right? Same idea. The only thing that was specifically related to what we have been doing was this idea that one perimeter would be the same thing as one revolution. Okay. We're going to stop here. In chapter 2, you guys should be able to do up through 24. This wouldn't be due until next Sunday, not this Sunday. So that'd be the 25th. So no big rush on that one, but if you're aching for some math homework to get started on, maybe after Thursday on the test day, you get home and you're like, man, I didn't get enough math today. I'm going to dive into that chapter 2 homework. I probably wouldn't look at this unless I had a lot of time unless I had time to kill, like I'm sitting at school anyways, and it's like, might as well just do this. Or, yeah, that's basically I would be worrying about the chapter 1 test until, before I'd be worrying about this, unless I have, I've done all my studying and I'm just sitting here doing nothing. Might as well get ahead because I know that I have grandma's birthday party next weekend or whatever, and I don't want to have to worry about this. Which is, that's fair.